Hi, welcome back. Today we're going to be looking at matrix multiplication. A country club pro shop sells 3 types of women's clothing. Tennis skirts cost $25 each, golf skirts cost $30 each, and tennis dresses cost $50 each. The table below shows the store's sales on Monday. Given this information, how much money did the store make that day? Well, the amount the store made on tennis skirts is calculated by multiplying 4 times 25, since she sold 4 skirts and they each cost $25. Then we'd have to add in the amount that they made on golf skirts, 2 times $30. Then we'd have to add in the amount that they made on tennis dresses, which is 1 times 50. So what's happening is that we are multiplying matching elements and then adding the products. Or put another way, we find the sum of the products. For this reason, this function in Excel is called a sum product. That's what I'm going to call this going forward. Trust me when I say you will absolutely need to know the function if you plan to work in an office setting in the future. The sum product concept is the basis of matrix multiplication. Back to the pro shop. What if instead of just one day, we wanted to know the total sales for the whole week? This just got a lot more complicated. Imagine if the pro shop sold 100 items instead of 3. See how time-consuming these calculations could get? Well, what if we took the numbers from the table and put it into matrices instead? Write a matrix for the information in the table, and then one for the prices. The idea is that everything in the first column is the tennis skirts, which cost $25. So all those numbers are going to get multiplied by 25. The second column is all the golf skirts, so everything inside of there is going to get multiplied by 30. And the third column are the dresses, which get multiplied by 50. But how can we be sure that we multiply the right numbers and don't mix them up? This is why mathematicians have a very special procedure in place for matrix multiplication. Let's take a closer look. The sales problem is a good example of why we might want to know matrix multiplication. Matrix multiplication is more formally referred to as the dot product, and we notate it using a big old dot. Now the next part is super important, so pay attention. Sometimes we can multiply matrices, and sometimes we cannot. The rule is the number of columns in the first matrix must equal the number of rows in the second matrix. Here are 2 examples. Do you see the difference? The order of the resulting matrix will be the columns of the first by the rows of the second. So if we take the dot product of a 3 by 2 and a 2 by 1, the resulting matrix will be a 3 by 1. This is a good illustration of why we use the dot to show multiplication in matrices. The cross sign is already used to describe the order of the matrix, so mathematicians try to avoid confusion by not using that same symbol. Let's look at a couple examples here for whether or not we can find the dot product, and if so, what the matrix is going to look like. So step 1, I want to identify the rows and the columns, the order of the matrix. So in this one, I have 1, 2, 3 rows and 1, 2, 3 columns. So this is a 3 by 3. Alrighty. And then in my second one, I have 1 row and 2 columns. So that's a 1 by 2. So step 2, once I have the orders, I am comparing these 2 middle numbers. They are not the same, so I cannot multiply. Cannot find the dot product, not possible. Okay, let's look at another one. Down here, number of rows is 3. Number of columns is 2. So there's a 3 by 2 matrix. I'm dotting with a 2 rows, 2 columns is a 2 by 2. All right, again, I am just comparing those 2 middle numbers. They are the same this time. So yes, we can find the dot product. And then if I want to know the dimensions of the resulting matrix, it's going to be a 3 by 2. So I'm going to have 3 rows, 2 columns. So I'd have a number here, number here, number here, etc. All right, one more example. These two look like they can be multiplied. They could certainly be added because we can tell they're the same order. We've got 5 rows and 1 column, dotting that with a 5 by 1. But even though we could add them, we can't dot product them because these numbers are not the same. So no, cannot multiply this one. Okay, last example. So once again, I am going to find the number of rows, 2. Number of columns, there's 3. So that's a 2 by 3 matrix. Same thing with this one. 1, 2, 3 rows and just 1 column. And so we notice we have 3 and 3 in the middle. So yes, they can be multiplied, dot product did. And the resulting matrix is going to be a 2 by 1. So that would look like 2 rows and 1 column. We'd have 2 numbers there. In a dot product, we multiply the elements of each row of the first matrix by the elements of each column in the second matrix. Then we add the products. So this 1 by 3 multiplied by a 3 by 1 ends up looking exactly like the sum product that we did with the store example. Calculating the dot product of bigger matrices gets a little more complicated, but it hinges on the same concept of the sum product. I know that the resulting matrix of this dot product will be a 2 by 2 with 4 elements. For the top left, I'm going to take the first row of the first matrix and sum product the first column of the second matrix. For the top right element, I'm going to take the first row of the first matrix and do a sum product with the second column of the second matrix. To calculate the bottom left element, find the sum product of the second row of the first matrix and the first column of the second matrix. Then to calculate the bottom right element, sum product the second row of the first matrix and the second column of the second matrix. Simplifying it all, I get to an answer. Probably seems like a lot, but once you've done a few of these practice problems, you will get the hang of it and it's going to become second nature. Before we move on, I want to go back to that same problem and do that multiplication in a calculator just so that you can see how it's done.
Just enter the matrices as usual. Go to second matrix, scrolling over to edit. I already have some matrices, which is fine. I'm just going to clear those out. We had a 2 by 2. Remembering to use the negative sign instead of minus. Okay, for the multiplication, I'm going to select, I want to multiply A times B, find the dot product. In the calculator, it's just going to be just like normal multiplication. We just hit the times sign. Then go back second matrix and select matrix B. And when I multiply those, it gives me the answer, which matches what we got before. What if we tried to multiply this 2 by 2 by a 3 by 1? So I'm going to take matrix A, multiply matrix D, enter, and it tells me there's a dimensional mismatch. That's what the TI is going to say when the matrices do not match up, so it's impossible to multiply them.
So the order in which you multiply the matrices does matter. This is in contrast to the commutative law for regular numbers.
We can also test the non-commutativity law here. Let's try it out doing it the backwards way. This time I'm taking matrix B times matrix A. I want to test and see if that's the same. A times B we have, what about B times A? Oh, there we go. We see here that these are not the same. So the order that you put the matrices in does matter.
I'm going to stop here. I hope that this was educational for you. Have a mathemagical day.